Around 2023, well, understands became the standard word for what large language models do. You hear it constantly. The model understands your query. It understands context. It understands nuance.
Right. But that word imported an entire cognitive framework. You're applying it to a system whose actual operation is quite different. The gap between those two things produces failure modes that are specific, predictable, and almost never named in the deployment conversation.
We are analyzing an excerpt from What AI Actually Knows, the attention mechanism. The premise is that applying human cognitive frameworks, words like comprehension and meaning, creates massive, expensive blind spots. We expect interpretation when we deploy these systems.
The vocabulary we use shapes the expectations you form about a system. It dictates your architectural decisions. Calling attention-based processing understanding produces a specific set of vulnerabilities. A transformer does not read your text, it weighs it.
I mean, across most tasks, that weighing produces something indistinguishable from understanding.
It does. But in the edge cases, the distinction is everything. To isolate what attention actually computes, we have to look at what it replaced. Before transformers, the dominant architecture for sequence processing was the recurrent neural network, the RNN.
Let us define how an RNN functioned. RNNs process text strictly sequentially. They evaluated token by token, maintaining a single hidden state that updated at each step of the sequence.
And that hidden state was supposed to carry forward the information needed from earlier in the text. Every time the model read a new word, it had to update this single mathematical representation. That design created a severe architectural bottleneck.
Because all context from everything that came before had to be compressed into one fixed-size vector. If you fed the model a long document, the summary of the first paragraph had to survive thousands of subsequent updates without being diluted.
For long sequences, that compression was catastrophic. Information from the beginning of document was progressively overwritten as the model processed more tokens. The hidden state functioned as a lossy summary of history.
It lost resolution with every additional word, which is a mathematical inevitability when dealing with a fixed capacity. So, attention was the mathematical solution to that specific bottleneck.
Instead of compressing history into a single vector, attention allows every token in the sequence to directly query every other token. It retrieves relevant information regardless of distance. The relationship between the token at position 1 and the token at position 500 is computed directly.
It is not mediated through 500 sequential updates. This direct querying is why transformers generalize better. It is why they scale and parallelize far more effectively than their predecessors.
Right. It is also the root of their specific failure modes. The direct connection circumvents the sequential bottleneck entirely, but it fundamentally changes what the model is doing to the text.
But if that's true, why isn't that comprehension? I mean, if the model can instantly connect a word at the end of a book to a word at the beginning, that sounds functionally identical to reading. How is that different from comprehension?
Because the connection relies entirely on vector geometry. It is pure math, devoid of semantic grounding. Each token in the input is mathematically represented as 3 distinct vectors: a query, a key, and a value.
We need to define those components clearly. The query represents what this token is looking for in the surrounding text. The key represents what this token offers to other tokens in the sequence.
And the value is the actual information this token contributes when it is selected by the mechanism. Attention is computed by taking the dot product of each token's query with every other token's key.
A dot product is just a mathematical formula used to score the alignment or compatibility between two vectors. It acts as a strict measure of relevance between the token asking a question and the token offering an answer.
That is precisely it. The system normalizes these compatibility scores using a softmax function. The softmax function converts the raw numerical scores into a probability distribution, ensuring they all scale proportionally between 0 and 1.
Which produces a set of weights across all tokens in the sequence. Finally, the model takes a weighted sum of the value vectors according to those normalized weights, so the output representation for each token is not a fixed static entity.
It is a weighted combination of all other tokens in the sequence. The weights reflect learned compatibility between query and key vectors. Bank as an example from the source text.
The word bank receives a different mathematical representation when surrounded by financial terms than when surrounded by river-related terms. That shift happens because the attention weights are computed differently given different surrounding tokens.
Yes, it is not because the model understands the conceptual difference between finance and ecology. It is contextualization. It is not comprehension.
The models learn statistical regularities from massive training data. They learn what words and concepts tend to co-occur. They do not learn logical relationships or causal dependencies.
A high weight between two tokens simply means those tokens tend to be mutually informative for predicting output in the training data. It does not mean they are causally related. Attending to one does not provide evidence about the other in any principled inferential sense.
Multi-head attention runs this exact computation in parallel across multiple independent subspaces. Each head learns to attend to different aspects of the input simultaneously.
One head captures syntactic dependencies, another captures semantic co-occurrence, another tracks corference, linking pronouns back to proper nouns.
The fact that some heads track syntax and others track semantics is just an emergent property of the training objective. It is not a deliberately designed cognitive feature programmed by engineers. A transformer stacks these attention operations deeply across many layers.
Early layers tend to capture local syntactic patterns. They track which tokens are grammatically related and which phrases cohere. Middle layers capture more abstract semantic relationships.
Later layers encode representations most directly relevant to producing the statistical output. By the time representations reach the final layers, they are highly contextualized. But contextualized does not mean correct.
The weights encode the statistical regularities of the training corpus. They encode what tends to follow what. This distinction between statistical weighing and comprehension becomes most visible when language models are asked to reason.
Transformers are pattern completion engines. Given a sequence, they produce a continuation that is statistically consistent with their training distribution. For a large class of reasoning tasks, statistical consistency is sufficient.
The patterns in the training data encode enough relevant logical structure that pattern completion produces correct answers.
But if that's true, why does it work most of the time?
Because the training distribution is vast. But that sufficiency is entirely contingent on the training distribution containing relevant patterns. When confronted with novel combinations of familiar concepts, transformers hit a structural wall.
Problems that require genuinely compositional reasoning expose the architecture. Compositional reasoning means taking known rules and applying them sequentially in entirely new ways. A 2024 paper proved that function composition is an architectural weakness of the transformer.
A single attention layer cannot correctly compose functions when the domain is large enough. The limitation remains empirically present even when domains are small. They cannot execute genuine compositional reasoning without prior examples to draw from.
But wait, Google challenged that assumption in 2022 with chain of thought prompting. They proved that if you simply ask a model to show its work, its math accuracy skyrockets.
The GPT-3 175 billion parameter model jumped from 17.9% to 58.8% on the GSM-8K benchmark of mathematical word problems. That is an improvement of 41 percentage points.
It was achieved from the exact same model with zero changes to its weights. Doesn't that prove it can reason? If generating steps improves accuracy that dramatically, it looks identical to logical inference.
The mechanism explains the jump. Chain of thought works because it forces the generation of intermediate steps. The model can then condition its next computation on those newly generated tokens.
Each intermediate step is just another pattern completion operation. The sequence of completions can approximate reasoning without any single step actually constituting it.
It succeeds because it breaks the problem into pieces that resemble patterns available in the training data. The intermediate steps act as a bridge of statistical familiarity.
Which is why chain of thought helps most on problems whose structure resembles patterns in the training data. It is least effective on genuinely novel compositional problems.
If neither the full problem nor its decomposition has close training analogs, the pattern completion engine stalls. True logical inference requires verifiable grounding in structural rules.
The model is simply generating the most statistically likely next step in a sequence. Benchmarks that measure performance on familiar problem types systematically overestimate reliability on unfamiliar ones.
The mechanism of chain of thought dictates its exact limits. It's not just an academic debate. The limitations of pattern completion are dictating capital allocation at the highest levels of the industry.
We should detail the reporting on Yann LeCun. He spent 12 years leading AI research at Meta. He founded Fair Air, shaping the company's AI direction for over a decade.
He left Meta in November 2025. In an interview, he stated that the industry's reliance on transformers is a dead end for genuine intelligence.
The source also notes his assertion that Llama 4 benchmark results had been fudged. The claim is that Meta used different model variants on different benchmarks to intentionally inflate the scores. We are reporting what is in the source material, not endorsing the claims.
In March 2026, LeCun launched AMI Labs. He secured $1.03 billion in seed funding. The explicit goal of AMI Labs is to build world models on DPU architectures.
This is a direct funded alternative to autoregressive transformers. Autoregressive models predict the next token based purely on the previous tokens. It is a massive financial bet by one of the architects of modern deep learning.
The bet assumes the gap between pattern completion and reasoning is real and insurmountable with current architectures. Scaling current models further will not close the reasoning gap. Closing it requires abandoning the transformer paradigm entirely.
The architectural debate addresses the future of the field. The mechanics of attention create immediate, systemic vulnerabilities for anyone deploying these models today. Transformer representations are context-sensitive by design.
The representation of a token is not fixed. It is a function of everything else in the context window. This allows the model to represent the same word differently depending on usage.
It resolves ambiguity and tracks coreference. But because representations are context-sensitive, they can be shifted by context manipulation. A model that produces a correct answer in one context may produce a different answer to the same question in a modified context.
That sounds like a retrieval problem, not a model problem.
It is entirely a model problem. You do not have to change the question to change the computation. You only have to change the surrounding text. The model has no architectural way to quarantine different parts of the context.
This is the exact mechanism behind prompt injection attacks. A document retrieved by a RAG pipeline may contain malicious instructions. The model processes those instructions as part of its context window.
Our RAID pipelines retrieve external documents to augment the model's knowledge before answering. The model attends to those retrieved instructions alongside your original query. The model has no architectural mechanism for distinguishing between authoritative instructions and content that just happens to be present.
Both are processed by the same attention computation. The query, key, and value matrices do not carry authority tags. Instructions embedded in retrieved documents redirect behavior because they alter the weights.
OSP identifies prompt injection as the highest priority vulnerability in LLM deployments. It is structural to how attention works.
So the fix isn't the model.
Right, and that doesn't fix itself. It is not an implementation oversight that can be patched with better filters. Sycophancy operates through the identical mechanism.
When a context implies that the user expects a particular answer, the attention weights shift. The weights move toward outputs statistically consistent with that context.
The model is not reasoning about what you want and deciding to comply. It is computing a continuation that aligns with the full context, including the implied preference. Changing the framing of a question changes the computation.
The model's answer is not a stable function of the question. It is a function of the entire context. Query, history, system prompt, retrieved documents, and everything in between.
Changing any of these alters the dot products and the resulting weights. The output is not retrieved from a fixed knowledge store. It is computed fresh every time, influenced by everything present.
System prompt design, conversation history management, and document ordering are not stylistic choices. They are the primary mechanism through which the model's behavior is controlled.
Measurement theory distinguishes between the construct and the operationalization. The construct is the abstract thing you are trying to measure.
The operationalization is the concrete procedure you use to measure it. A good operationalization captures the construct reliably. A poor one measures something that correlates with the construct without being the construct itself.
Attention is an operationalization of something that resembles understanding. On a remarkable range of tasks, it correlates with comprehension, but it is not comprehension itself.
The construct and the operationalization diverge in specific, predictable circumstances. Novel reasoning problems, precise factual claims, context-sensitive manipulation.
Those circumstances are precisely where the stakes of the divergence are highest for your deployments.
A transformer weighs your text. Across most of what you ask it to do, that weighing produces something indistinguishable from understanding. Across the rest, the distinction is everything.
Fine-tuning a system on your corporate data does not teach it the truth. It simply hard-codes an entirely new set of blind spots.